Hi guys, it has been more than 2 years since any videos. A lot of personal issues and pandemic hasn't been helping with creating any content either. So yeah, I actually created this channel just to share ideas about do-it-yourself audio and maybe some professional audio content. But mostly I created it just to keep kind of like a video logs of build progress and just to share with my fellow workmates and other hobbyists what I've been up to. About 2 years ago, I noticed Italian loudspeaker manufacturer Faital Pro has been releasing a lot of interesting drivers, and one of them was a 12-inch PA subwoofer. What makes this driver very unusual is its power handling and other TS parameters. Actually, this driver really caught my eye because it can be put in like a really small enclosure and it's actually performing like really well. Should be, at least on paper. This video will be split in like 4 parts, I think so. Number 1 would be like idea and simulations. Second part would be problems with the printing it. Third part will be hopefully some measurements, and the fourth part I think will be conclusions and maybe some additional content or something that I might miss up on the way. As I said, idea behind this subwoofer came around 2 years ago when I noticed that Faital is launching like new line of very powerful speakers, and one of them was 12-inch and the second one was 15-inch, and sometime later they released a new 18-inch driver also. However, on the practical side, 12-inch really caught my eye because that's like almost to the limit that I could print with my 3D printer. I have been doing a lot of speaker enclosures and systems with my 3D printers. However, I have never done like a PA subwoofer, especially with this power handling capabilities. So that was quite of a challenge to try to do it. I quickly realized that it won't be printable in one piece as I first wanted to. I decided to split it in 4 parts. One would be like the front side, the middle side, the back side, and the port would be fourth component. All my systems have laminar flow type ports, and comparing to ordinary ports, they're way more efficient. They have about 30% less distortions comparing to the same size, same tuning, like pretty much same everything. They're a bit more efficient. In my experience, it's like a couple of dBs. However, my colleagues, they have noticed that the port itself is about 6 dB more efficient than ordinary port. So it's a no-brainer to actually print all my ports laminar. So this is the driver I'm talking about. As you can see, large magnet, robust chassis, good surrounds, everything. So yeah, quite a powerful beast. As you can see straight away, 1.4 kilos of AES power, 2.8 in the peak, sensitivity of 92, 50 hertz FS, was about 25, X max 12.5, and QTS of 0.42. So quite an interesting thing. Only downside, as you can see, it's 8 ohms. My guess is that 8 ohms was preferred to keep the BL parameter up, because if you go with the lower, let's say 4 ohms, it's easier to drive it with the amp. However, you get less control there. So that's my hunch why it's 8 ohms only, no other available impedances. However, here it's quite okay up till like 1K. It's reasonably fine, maybe even 2K. I don't know how it will actually sound here, but it could be feasible to actually do like a two-way system with a ordinary compression driver. So we're in my beloved Win ISD. As you can see, it's -3 point is about 45 hertz. So that's quite remarkable of such a small driver. Volume is about 23 liters and tuning is 47. That was what the software suggested. So we could round it up to like 25 and let's say like 50 hertz to get a bit of boost here. So yeah, that's pretty looks good. However, pretty rarely subs play higher than like 20 something hertz depending on the rest of the system. So let's slap on the low pass at 120, like pretty standard, I would say, and a high pass. Okay, I will show you how did I get that high pass. So cone excursion with the signal of AES power. If we put the 40 hertz fourth order filter here, everything's within its theoretical linear range. So at SPL, it's about 120, 122 with the AES power. Sounds good. Yeah. Once we get to the airspeed at the port side, it looks ugly here. You see, at already quite a big port, it's still 48. Let's go to like 15 centimeters, and that's a bit too much. 13. Okay, let's keep it 14 just to be safe. There are many rules of thumbs on the internet about air velocity in the port, or the airspeed, how it's called. However, we can see if the vent is about 14 centimeters and the length is about 63 centimeters, so it's quite a giant port, and it's still around 30 meters per second. So for the ordinary port, that's quite bad. Like one rule of thumbs that I have heard, that you should stay below like 10th of the speed of sound. So that means like below 34 meters per second. There are even more conservative ones that you should stick below like 20 something meters per second. However, on my measurements about the laminar flow ports, I can go actually up till like 60 meters per second. So you can see, let's say I'm just below 60 meters per second of the airspeed in the port. And the port length is almost, oh no, it's actually more than cut in half. And I'm still getting no noticeable turbulence in the port. I will try to back this up with measurements. This prototype, I kept it below 50 because I wanted to maximize the length of the port that I can stick in the box. So I went with the 11 centimeter port. So yeah, I will show you. This is actually what I came up with. As you can see, I'm maybe losing 2 dBs of efficiency. However, my -3 point is just right about 40 hertz. It isn't a massive difference, however, it's just a choice I went with. It might be possible that on some further prints I might modify the box size just to tweak some parameters around, and that's it. However, yeah, the excursion is a bit higher. However, it's still under theoretical linear limit. So, about the SPL, at AES power, it's roughly about 120. However, that's at 1 meter. No one's gonna listen to it at 1 meter. So we might. Okay, so this is a pretty usual listening distance at 10 meters, let's say. And still at 10 meters, this one single 12-inch sub goes around like 100 dBs, give or take. As you can see, the box is quite deep, a bit more than 60 centimeters. And majority of that is the port. However, on the upside, because of laminar flow port, I can still keep it reasonably short. Looks like I have went with a 42 centimeter port. After I decided for a bigger box, I realized that it will be impossible to actually print it in one piece. So I split the whole thing in 4 parts. The majority of the port, the back end with the port, middle, and the front end. Once I realized that it will be impossible to print it in one piece, I started to fiddle around and try to figure out how could I make it either faster or cheaper or whatever. I realized I can make walls a lot thinner. At this point, they're like only 2.5 millimeters. So that's nothing. That's not okay even for like ordinary house speaker, let alone the powerful subwoofer. And I decided that I will actually print it as a shell, glue it together, and then afterwards I will fill all of these sides with polyester resin and a filler, of course. So this will become as a composite shell, I would say, or composite enclosure, because the shell would be 3D printed. All the openings and everything will be defined by a printed shell. However, the most of rigidity and water tightness will be given by the polyester resin. I don't remember exact amount of print time. However, it was probably around 10 to 12 hours per each part, and took around, I think, a bit more than kilo for each part. On my next video, I will try to show you the process of making the enclosure, gluing it together and filling with resin. So, see you next time.